Few announcements before we start. One, just a reminder, homework 3 is due on Thursday. Let me know if something is unclear. Feel free to ask a query on Slack, office hours, discussion, whatever you prefer. The grades for the midterm are posted on Canvas. Take a look. The mean is 27.18. Standard deviation is 7.3. And just to connect it to what we are doing, the mean is, of course, expectation of x, where x is a function from the space of students to real numbers or scores. And so that's just a random variable with the outcome space that pick a random student and look at the score. And standard deviation is just square root of the variance of x. So, and I mean, the scores were fine, great. If there was something which you maybe missed in the midterm, or maybe the score was not what you were expecting, feel free to take a look, discuss the exam with me if you like. And I mean, in terms of percentage for the course, the midterm is slightly more than a homework, so it's not sort of a huge worry if it did not go as well. But do think about what are the concepts which maybe seem problematic in terms of the midterm, and we'll discuss the solutions towards the end of the lecture. So we'll go over sort of a quick recap of the midterm, but feel free to discuss more if you want. On that note, sort of maybe a slightly unexpected trip, but I'm in India for the next few weeks. I was just checking if it's possible to move the office hours to 12 to 1 on Wednesdays. I mean, the day is the same. The time is 12 to 1 instead of 3 to 4, so that it's not 2:30 a.m. for me. But if in case this is a problem, or in case you can't make it to the new time, let me know. I'm not changing anything on Canvas. This is just a question for you. If it's a problem for anyone, feel free to let me know. I will not change anything on Canvas or before the end of the day. So just and I will be available after the lecture also to discuss more if you like. So yeah, we can keep the original time in case this is a problem for anyone at all. Okay. All right. Let's continue with applications of probability. Also, yeah, since I'm traveling, in case there's any connectivity issues or in case you don't hear me well, just let me know. Let's continue with the applications. And today I want to show some applications of the relatively sort of basic concepts in probability that we have developed, just the notions of conditioning, expectation, and random variables, events, etc. So, but even these concepts by themselves can have fairly powerful applications, and we'll see a few examples. The first is what is called, or what I will call, the polynomial identity lemma. This is kind of maybe the inverse of the homework problem. In the homework problem, we're kind of asking the question, if you fix an input and pick a polynomial at random, what is the chance that the value is A or something else? Here, we're asking the opposite question. If you fix a polynomial and choose a random input, what is the chance that the value is something in particular 0? You can use the same equation to study other values. This is often called the Schwarz-Zipple lemma, or the Dimilo-Lipton-Schwarz-Zipple lemma. But it turns out that the lemma itself has a fairly long history, and it was rediscovered independently many times, at least going back to the 1922 and probably even earlier. So and ladder reference in case you're interested in reading about some of the history. I mean, this lemma itself is the workhorse of algebraic coding theory, of sort of many applications in complexity theory. It's a very simple bound, but it's surprisingly useful. And we'll see that the proof is also very elementary. Okay. Okay, so let's go over the content of the lemma. And yeah, just because it has a fairly long history and it's maybe not feasible to name all the authors in the name of the lemma, we'll just call it polynomial identity lemma. The content is the following. Suppose we have a polynomial in n variables. So not a polynomial of a single variable, but n variables. And over any field, and you can think of the field as finite or not, depending on what you like, but you can think of the field FP if you prefer finite fields. You just have to think of P as sufficiently large, and we'll see. And a polynomial in many variables, as before, is just given by a sum of now monomials, where each monomial is of the form x1 to some power, x2 to some power, so on. And some of these powers might be 0. So if the variable doesn't appear, we'll think of the power as 0, such that the sum of all the powers, which is the sum of all the exponents, is at most t. So this is what we'll define as the degree of the polynomial. And each monomial is multiplied by some coefficient. The question we are asking is, what is the chance that when you choose x1, x2, x3, and so on independently at random, what is the chance that the polynomial evaluates to 0? Okay. Another way of asking this question is, how many roots does the polynomial have? In like a root for a polynomial in n variables is just a collection of values for x1, x2, all the way to xn, where the polynomial evaluates to 0. And so we're asking, how many roots does this polynomial in n variable have? Interested in a slightly more specialized version, or I mean, the proof is kind of equally easy for this more for the stronger version, where we are only checking what happens when x1, x2, and x all the way to xn are chosen from some special set S, which is a subset of the field. So in case the field is infinite, like real numbers or complex numbers, the lemma can still make sense if you pick some subset of size 23 or whatever, some finite set, and then choose x1, x2, and so on independently from this set. Okay. And this is just counting how many roots are there, where x1, x2, all the way to xn are all inside this set S. Is the statement of the lemma okay before we continue? Okay. Right. We'll prove it by induction on the number of variables. So let's say the base case for the induction is that we have a polynomial in one variable, which is a case we are already familiar with. And we are picking a value for this variable uniformly and randomly from this set S. So pick each element of the set S with equal probability. And what is the chance over this random experiment that we pick a value for x1, which is such that the polynomial evaluates to 0? Okay. And what we want to prove is that this is d divided by size of S. In fact, we want to prove this over x1 to xn. The definition of d will depend on whether we have one variable or more variable. It's the sum of, it's a bound on the sum of the exponents. So if it's just one variable, this is the usual notion of degree for a polynomial. Okay. Any guesses or suggestions on how to prove this? This is what we want to prove. I haven't written down a proof yet. So this is an event, which is really, this is a shorthand for a subset of the outcome space. And here I'm implicitly thinking of the outcome space as which is nothing but what are the outcomes for each variable, for this one only variable x1, which is the only variable in our polynomial right now. And the probability measure is just 1 over the size of the outcome space, or 1 over the size of S, right? So, and the event we are talking about is the subset corresponding to the subset of values where the polynomial evaluates to 0. And we are trying to calculate the probability of this event. Another way to write this subset, and this probability is just one over size of S times the size of this subset. And let's write the size of this subset in a slightly more involved way. So instead of looking at all values in the set S, let's look at all values in the entire field such that the polynomial evaluates to 0. And let's take the intersection with the set S afterwards. And we are asking what is the size of this set. I claim that we already know a bound on the size of what is in the first bracket, which is just the number of roots of a degree D polynomial in one variable. This we saw Lagrange interpolation. This was maybe something you also used in the midterm. And we know that this is at most D for a non-zero polynomial. If the polynomial is 0, then of course every point is a root, or it always evaluates to 0. But we were given non-zero in the statement of the lemma. Otherwise, the problem is trivial. It's the probability is 1. It always evaluates to 0. Okay. And if the first set is less than equal to size D, or like the size of the first set is less than equal to D, then the whole thing is less than equal to D. So this is less than equal to. Any questions on this? Okay, so then let's maybe switch to the more interesting part, which is the induction step. So let's say we assume this bound for any polynomial in at most n minus 1 variables. And now we need to prove it for a polynomial in n variables. So and the induction step is just an application of law of total probability, or what happens if you want to write an event as conditioned on another event. So we know that for any event B, we can write down the probability of B as first seeing what is the probability of B, just looking at the part of space corresponding to A, and then looking at the probability of B in the part of the space corresponding to A complement. Okay. So this way, you know, for any two events A and B, and now we'll instantiate it with some special events which are suitable for this purpose. So let me define B as just the event we want to understand anyway, which is just that f of x1 to xn is equal to 0. And now, again, for this part, I have implicitly chosen the outcome space to be the set of values or set of outcomes for x1 to xn. And the probability measure is that each outcome where x1 to xn are assigned from the set S is equally likely. And I mean, you can work with a different outcome space if you like, but the probabilities of these events will be the same in any outcome space which is representing the experiment we just described. So you can work with a different space if you prefer. Okay, now the event A is something I'll kind of define based on the structure of the polynomial. So the polynomial f, you can write it as sort of a sum of monomials with different powers. And now either the variable xn appears in at least some term or some monomial, or it doesn't appear at all. If the variable xn does not appear anywhere, then this is a polynomial in n minus 1 variables. We are done. We can go home. If it does appear with, but when I mean it does appear, it just means that there is some monomial in which the exponent of xn is strictly bigger than 0. It's either xn to the power 1, xn to the power 2, or something. Let's call the largest exponent k. And it's greater than 1, otherwise we are already done, and the polynomial only depends on n minus 1 variable. So greater than 0, sorry. So now let's just factor out xn to the power k in all the monomials in which it appears and collect what remains. So what remains after I have factored out xn to the power k in all the terms in which xn to the power k appears will be some collection of monomials in x1 to xn minus 1, a bunch of other terms. I'll just collect them all together. And this is just another polynomial in x1 to xn minus 1. Importantly, the degree of this polynomial will be less than equal to d minus k, because the sum of powers of all monomials was at most d, and I factored out xn to the power k. And let's say rest of the terms, everything that remains is what I'll call h. It's some other polynomial in x1 to xn. Is that okay? Just a decomposition, just a definition of g and h. Okay. Now, let's compute these monomials, and so we want to understand the left hand side, and there are 4 things on the right hand side which we need to understand to be able to bound the left hand side. For some of them on the right hand side, I will use relatively simple bounds, and we'll see what remains to be computed. Okay. Let's see. The probability of B given A, or in fact, any probability, is at most 1. So let me just use this simple bound on this term. The probability of A complement, I will also use that it's less than equal to 1. Again, nothing very sophisticated. And now I claim that the probability of A, we already know how to calculate. So the event A is that some polynomial in n-1 variables of degree at most d minus k is equal to 0. And since it's a polynomial in n-1 variables, we already know how to calculate this probability from our induction hypothesis. This is at most the degree of the polynomial divided by size of s. Because each of these n-1 variables are being chosen, again, uniformly and randomly from s, even for this polynomial g. Okay. And what remains is this final term of what is the probability of B given A complement. Any questions on what we said up to here? Okay. Now, let's see what the probability of B given A complement is. So what does it mean that we are conditioning on A complement? We are conditioning on, or we are restricting ourselves to some subset of omega where we are restricting ourselves to some subset of omega where we know that G does not evaluate to 0, right? Because that's what A complement is. Now I claim fix any such, and importantly, this restriction does nothing for xn. Xn is still chosen uniformly and independently from the field, even when I look at this subpart of omega, because the conditioning is only in an event which depends on x1 to xn minus 1, because x1 to xn are all independent. Conditioning on any specific subset of x1 to xn minus 1 does not change the distribution of x1 of xn. So fix any values of x1 to xn minus 1 such that the g does not evaluate to 0. What you have now is a polynomial only in the variable xn, because we have fixed x1 to xn minus 1. So once you fix x1 to xn minus 1, this is a polynomial only in this one variable. Here also you can write down whatever terms involve xn and think of the rest of them as fixed coefficients. Okay. And And because we know that at least one coefficient of this polynomial is non-zero, which is g of x1 to xn minus 1, we know that this is a non-zero polynomial. And we know that the degree of this polynomial is equal to k because the highest power of xn that we have is k. So now we have a polynomial in one variable. We are asking what is the chance that if it evaluates to 0, well, again, we know the answer from induction, which is the degree of the polynomial divided by the size of s. So we know this one missing term, it's less than equal to k divided by the size of s. And that's it. I mean, when we sum these up, we will get the probability of b, which is what we wanted to understand, is less than equal to d over s, which is what we wanted to prove anyway. Any questions?
I have one question.
Yeah.
When you condition on a complement, that only tells you that you want your g to be not equal to 0. Why does it say that your g has fixed coefficients?
I'm not saying g has fixed coefficients. You mean, why does it say that when I think of the value of g as a coefficient, why is it fixed rather than right?
Being
So here,
a set. Yeah.
Yeah, right. So here I am sort of implicitly doing another application of law of total probability. So when I look at this new space, which is the outcome space corresponding to a complement, I'm partitioning it into some other pieces f1 to fr for some r, where each corresponds to a value of the tuple x1 to xn minus 1, which is in a complement. So this is a partition for every different value of x1 to xn minus 1. I look at all the outcomes in the outcome space now corresponding to a complement and split them into these kind of smaller events, which are f1 to fr, which partition a complement. And what I'm really saying here is that the probability of b given a complement is equal to the summation of the probability of fi given a complement times the probability of b given fi. I don't need to condition fi on a complement itself because they're subsets. And this is something which we saw is generalization of the law of total probability to more than two things. In particular, all I'm saying is that this outcome space can be thought of as this green region can be thought of as comprising of smaller regions based on every possible value of x1 to xn minus 1, which is compatible with g not evaluating to 0. And each small piece if I just look at that piece and say, what is the probability of B happening in that small red piece? It's less than equal to K over the size of S. And so it's also true when I look at all the collection of red pieces as an aggregate. Does that make sense?
Yeah.
Okay. Yeah, but it's in each one of these small pieces that x1 to xn minus 1 are fixed, because that's just the definition of these pieces. Yeah, not in the green piece as a whole.
One more question.
Mm-hmm.
So
Yeah.
G sort of fixed. You want you get the first term is only varying in xn, but
Yeah.
what if you want your f to be 0, you also want h to be 0 simultaneously?
Yes, you want h to evaluate to 0. Yes.
So
And
is that also 0 by the same reasoning that x1 to xn minus 1 are taking distinct values which are kind of fixed, and then it
right. So
becomes
once you fix x1 to xn minus 1, this term is also some collection of monomials which involved x1 to xn, all of them, and you have fixed n minus 1 variables in all of these monomials. So each of these monomials only has one variable which is free, which is xn. So these are all monomials in one variable xn with a new coefficient which comes from x1 to xn minus 1. I don't know what these coefficients are, and I'm not even sure if they are non-zero. But if I look at the whole aggregate, if I look at the entire collection of the monomials I get from the first part and the second part together, this whole thing is one polynomial which has at least one coefficient which is non-zero.
Okay.
Right? And as long as that is the case, I know how to compute the probability. That makes sense?
Yeah.
Okay. Okay. Maybe I'll elaborate on some of these things even in more in the notes, so that just this application of total probability is clear. Okay. This application itself has applications in the sense that this polynomial identity lemma is, as I said, a fairly useful tool in algorithms, in coding theory, in sort of property testing, whatever. So one kind of simple use of it is to check if a bipartite graph, which is just a graph with two parts, so we have subsets of vertices u and v, and edges which go from one piece to the other, but not from one vertex in u to another in u, or from v to v. And so if we have such a bipartite graph, a question which is useful in modeling various things is there a perfect matching? And a matching is what it sounds like, that we are able to match each vertex in u to a unique vertex in v, and vice versa. Or in other words, we can pick according to edges in the graph. So we can pick a subset of edges in the graph, which we think of as all possible allowed matches, sort of the edges in the graph. And for each u, we pick a unique v. For each v, we pick a unique u. So it just means that for each vertex, there is exactly one edge in the subset which is picked, which is kind of the assignment of that u or v. And yeah, maybe examples you might have seen sort of stable matching algorithms, which supposedly used to match if, applicants to medical schools or residents and so on, where you probably sort of have some matching between the slots and the people you are taking, so that each slot is filled by exactly one person, and all the people you want to take kind of end up in one slot. And for this to make sense, of course, we will have to have that u and v are of the same size. Otherwise, you can't match exactly each element in u to exactly one element in v. And let's just say this size in n just for convenience. So given a graph, a bipartite graph, if I tell you all the edges, it's not always obvious to see that this has a matching or not. And this can be tested in polynomial time, but using what we just described in terms of polynomial identity testing, you can get a fairly simple randomized algorithm, which turns out it can also be parallelized. And this is basically the only kind of efficient parallel algorithm we know for this problem. It's I mean, to some extent, you can do this without randomness. It's a huge question, a huge open problem to see if you can do this without randomness in some sense at the same level of efficiency as a randomized algorithm. I won't get into those details, but there is a relatively simple algorithm for checking this. If you allow me to use randomness and using what we saw about polynomial identity testing. Just to point out, the graph that I just have here does have a matching. The trick is that if you think of the vertices of the graph as the field elements of the field F7, and you think of matching the number A to 2A, then it has a matching. So 0 matches to 0, 1 matches to 2, 2 matches to 4, and so on. So, and you can check that, I mean, kind of made this graph up so that it has this sort of a matching. 3 matches to 6, 4 matches to 1, 5 matches to 3, and 6 matches to 5. So each vertex has exactly one edge incident on it. I mean, by the way, the fact that when you map A to 2A or A to 3A and so on, the fact that these are all matchings is also the proof of Fermat's little theorem, if you want to think about it. So it's I mean, yeah, it's not something we need necessarily, but it's not a difficult step from here to the proof. Okay, going back, the way to apply this kind of knowledge about polynomials is to, well, create a polynomial out of this graph. And the way we'll create the polynomial is actually by first creating a matrix of variables. So it's a matrix, but entries of this matrix are not a matrix, are not numbers, but variables. And the way we will sort of define an entry is that the entry ij, ith row in the jth column, is defined to be xij, the variable xij. So for every ij, we will create a new variable, let's say, and we will write down xij as a variable inside this matrix. If ij is an edge, and here, I mean, I is in U, J is in V, so this you can think of as a directed edge if you like, but I and J are in different subsets. And 0 if there is no edge. So the entries of this matrix are either variables or zeros. This is sometimes also called the Tut matrix. And you don't need to know the name for the application, but and so just as an example, x11 or the 1, 1 entry, because we do have an edge between 1 here and 1 here, this will be a variable. X12 will be 0 because we don't have, or maybe I should, yeah, x12, because we don't have an edge between the first vertex here and the second vertex here. There is no edge, so we will put in a 0, and so on and so forth. So we can complete this matrix. Okay. Is the definition of the matrix okay?
Yeah, just quick, I guess it's not clear why is x11 a variable as opposed to just like 1 or just like some flag.
Right, so, right, so if you, I mean, I wanted to define, let's say, the incidence matrix or the adjacency matrix of this graph, I would put in x11 as 1, and if there is no edge, I would put in a 0. I'm choosing to create a matrix of variables, and we'll see in a minute why this matrix is useful. But right now, I mean, the fact that x11 is a variable is just how I'm choosing to define this matrix. So it's sort of almost by fiat that this is a variable. And so I have sort of these n square variables at my disposal, if you will. And whenever there is an edge, I put in the appropriate variable in that entry in the matrix. When there is no edge, I put in a 0. And so this gives me some matrix which has some of these variables out of my collection. And what I do with it is for later. But right now, I'm just constructing it to be a matrix of variables. Is that okay?
Yep, sounds good. Thanks.
Okay. Now, here is the reason why having this matrix of variables is kind of nice. I claim that the graph G has a perfect matching if and only if the determinant of this matrix of variables, and determinant is something we haven't discussed in this course, and we don't need it for the linear algebra part we covered in the course, but I'm guessing almost everyone has seen determinant at some point or the other. And you can, for any matrix, you can sort of compute it by this kind of row and column expansion kind of formula, or you can use the fact that the determinant is nothing but you choose some permutation which maps the set of rows to the set of columns, and you write down from the, so you basically pick one entry from each row and one entry from every column, and you multiply those entries and multiply them with some sign. So for the first row, let's say I'm picking the entry pi1. From the second row, let's say I'm picking the entry pi2. And because also I have to pick one unique entry from every column, this is a permutation. I can't really pick second entry from the first row and the second entry from the second row. If I pick the second entry from the first row, I have to pick something different in the second row. So that's why there is a unique entry in every row, and then that's what a permutation is. And then here there is some there is some number which is either plus or minus 1, which depends on this permutation. I mean, this is just an expression for the determinant. In case you've already seen this, you might be familiar with it. If not, I'll just claim that this is sort of one way of writing the determinant, and we can go into it later. But suppose we could write the determinant in this way. Now, because our matrix has variables in it, this determinant is not a number, but a collection of products of variables. So it's a polynomial. Because each of these terms in the summation is a monomial, and a sum of bunch of monomials is a polynomial. It's a polynomial in these variables xij, where I is in u, j is in v. And moreover, if there is any term, any monomial which appears with a non-zero coefficient, then there must be a matching in the graph, because, well, almost the way I wrote it in terms of each term corresponds to a permutation. And permutation is just another way of saying matching in disguise, because if you go back to what we wanted here, we wanted to map each vertex in U to a unique vertex in V, and the size of U and V were equal. So that's just what a permutation is. You put the vertex 1 on the first place on the right hand side, you put the vertex 2 on the third place on the right hand side, and so on. So it's a matching and permutation are the same thing. And if we do get a non-zero monomial, then if this monomial is non-zero, if and only if ai and pi of I are is not equal to 0 for every I. So it's a product of variables or a product of entries of the matrix, and each entry has to be non-zero for the product to be non-zero. And this happens if and only if I comma pi of I is an edge, because when there is no edge, I put 0. So this is non-zero if and only if there is a matching which corresponds to the permutation defining this term. And what I've left out is that because I defined this matrix in terms of variables rather than numbers, different terms cannot cancel each other. And that's something to think about. So because different terms will involve different variables. So there will be no two terms which involve exactly the same set of variables. And so they cannot cancel. This is something to think about. So if we have this claim, which is up to this thing that I left as an exercise, what we have now is that there is a polynomial which we have defined. I don't yet know how to calculate it, etc. That so this polynomial is not identically 0, or it's a non-zero polynomial if and only if the graph has a perfect matching. Is this claim, is it okay that this is a restatement of what I wrote on the slide? Okay, I'll take that as a yes, but stop me if that's not clear. So checking if the graph has a perfect matching is equivalent to checking if this polynomial is not identically 0 polynomial, or it's a non-zero polynomial. And the way I wrote it, computing this polynomial is a bit of a problem. It has too many terms, possibly n factorial, depending on if you're writing this in this kind of ugly long way in terms of all summations. But what we do know is that if we have a matrix of numbers, then the determinant can be calculated efficiently, and this is something which is used a lot in many algorithms. So in fact, it turns out this sort of operation can also be efficiently parallelized and so on, which is the sort of reason we get a parallel algorithm out of this whole thing. And now the only thing that we need to know is to apply our lemma is the fact that we can also understand the degree of this polynomial.
One thing that's unclear to me is you showed that there is a matching, but we haven't showed that there is a perfect matching. If the
When I said there is a
determinant-
matching, I meant a perfect matching, because a permutation is the same as a perfect matching. Because for every I, I'm finding a unique pi of I, because pi is a map. It matches every I to a unique pi of I. And because I assumed U and V were of equal sizes, every permutation also has an inverse pi inverse. So this is a one-to-one correspondence. A permutation is a bijection.
Okay, yeah.
Good. So yeah, I mean, when I say matching here, I mean perfect matching, just because we have taken U and V to be of equal sizes and so on, and I do mean sort of a permutation which defines some match for every element of U, and because of the same sizes, also some match for every element of V. Okay, and we said that this is equivalent to checking if some weird degree n polynomial is the non-zero polynomial. And we don't quite know how to write down this whole degree n polynomial. It's probably too sort of complicated to write down in its full detail, but we can evaluate it. If I plug in the values for the variables xij, if I give you some value for each variable, then I will get a matrix of numbers. And calculating the determinant of a matrix of numbers is easy. So the fact that I can calculate this means I can evaluate the polynomial efficiently for if I plug in some values to each of these variables xij for I in U, j in V. Okay. And what the polynomial identity lemma tells me is that if I have a set S and if there is a perfect matching, then the polynomial is a non-zero polynomial. And if I evaluate it on a bunch of values, then the probability that I will get the output 0 is less than equal to the degree of the polynomial divided by the size of the set S. Okay. So pick any S. Pick any set from which I will choose the value for every variable. Let's say this is picked to be greater than 10 times n. So pick, and then this probability is less than equal to 1/10. So it tells me that if the polynomial was non-zero, I plugged in random values into the variables defining this matrix, calculated the determinant of this matrix that I got. The probability that the determinant will evaluate to 0 is at most 1/10 if the graph had a perfect matching. On the other hand, if this was a zero polynomial, the probability that it will evaluate to 0 when I plug in values for the variables is 1. It will always evaluate to 0. So this is a randomized algorithm for distinguishing the two cases. Okay. Given a graph, define this cut matrix, pick some set of values which you are going to choose for each variable independently, large enough set S, and plug in the values. Pick random values for the set S independently for each variable, and then plug them in, compute the determinant. And if it's 0, you can be reasonably confident that the graph did not have a perfect matching, because if it did have a perfect matching, the chance that you will get 0 is only 0.1. So hopefully not too bad. You can, of course, take the set S to be even larger if you want to be really confident. You can also repeat this experiment a few times, and we'll see later how that helps you improve your confidence. But this is the algorithm. And as I said, this algorithm is, I mean, once you get past the definition of this matrix in terms of variables, etc., the algorithm is really simple. Plug in random values and see if the determinant is 0 or not. And it can be efficiently parallelized. It has some other sort of theoretical as well as useful applications. So this is just an example of the polynomial identity lemma in action. Any questions?
What's the computation complexity for calculating the determinant?
Right. So, I mean, naively, I haven't said anything, but it's at least polynomial in n or n cube is sufficient. But yeah, you can don't remember exactly how fast you can do it, but you can speed it up beyond that. I can try to write this in the notes. So yeah, I don't remember exactly what's the fastest now. Okay. The next thing I want to talk about is what's called the probabilistic method, which again is just an application of computing expectations. So really speaking, it's what's called the first moment method, or sort of a very special way of applying the probabilistic method. There's a beautiful book by Allen and Spencer. I think I mentioned it in the resources section on the course webpage, which has many kind of stunning applications of this principle, and I highly encourage you to take a look. But the very vanilla version which I want to discuss is just the following. If you have a random variable, which is nothing but a function on an outcome space to real numbers, if the expectation of this random variable is greater than equal to some number c, let's say a real number, let's say there's a variable maps to real numbers, then there is an outcome where x is greater than equal to c. Because, well, if not, so if x of omega is less than c for all omega, then expectation of x, which is equal to summation nu of omega times x of omega, will be less than summation nu of omega times c. And just because summation of nu of omega is 1, this will give me that expectation of x is less than c, which is not true. We assumed it was greater than equal to. This is a principle, or this application we've used many times, just that if you have an average of a bunch of quantities greater than something, then at least one of the quantities is greater than the bound. We also used it in analyzing the Rayleigh quotients. We've also, one of the problems, which was basically a Rayleigh quotient kind of problem in the midterm, also you can use this kind of idea to solve it. The same holds if you have expectation of x less than equal to c, then there exists an omega such that x of omega is less than equal to c. The same proof. Can you say it for equality? If it's true for greater than equal to, if it's true for less than equal to, is it true for equal to?
No.
No. Yeah, I mean, it's very easy to see that this is false, but still this is a mistake which happens. I just wanted to point it out. I mean, think of a variable which is 0 with probability half, 1 with probability half. The expectation is half. There exists an omega, namely 0, where x of omega or 0 is less than equal to half. Yes. There exists an omega where x of omega equal to 1 is greater than equal to half. There is no outcome when the random variable is equal to half. It's always either less than half or more than half. And so the point is that when I say there exists omega for the greater than equal to part or less than equal to part, these can be different omegas. They're not necessarily the same omega which realize the greater than equal to and less than equal to. Okay. Yeah. It did not say anything very deep here, but it's still kind of surprisingly useful. And it's useful to kind of show the existence of some object just by computing the expectation of some kind of property we want this object to have. And once we can prove a bound on the expectation, we say that, okay, there must exist an object with this property, without even having to think about what this object must look like, sort of how should it be that this object can be designed to satisfy this property, nothing. And so it's useful in many proofs of showing that something can be done without sort of figuring out exactly how to do it. And then sort of that it's called a non-constructive proof. And then sometimes it can be much simpler. I mean, also, probably doesn't give you as much information if you knew how to do sort of how to get this property, but still, it's very useful to show the existence of things. One example where actually we can also kind of turn it into an algorithm for finding the thing we want, but let's start from just existence. So is what is called what's called the 3-SAT problem, and or specifically the version which is called max 3-SAT. So 3-SAT, again, this is something which you probably have seen in any class which talked about NP hardness, NP completeness in undergrad. So a 3-SAT formula is just a logical formula where which is an AND of ORs. And let's say it's a AND of M things. Each of them is an OR of exactly three things which are called literals, which is just kind of a short way of saying the thing in that position is either a variable or its negation. So, for example, you can have this kind of a formula, which is x1, or this is the negation of x9 bar, or x2, and x5 or x2 bar or x3 or whatever. So it's a collection of these ORs which are called, and these things are called clauses. And the variables or negations appearing inside every clause are called literals. And we are restricting ourselves to the case when each clause has exactly 3 literals. In general, when we talk of 3-SAT, it's at most 3, but it's simpler to work with this for now. Okay. And the maximization version. So when we usually say 3-SAT, it's about, can we assign all the variables to true or false in such a way that all clauses are satisfied. So that's why we are writing an AND of ORs. And in the maximization version, we don't quite think of it as an AND, but rather lists separated by commas. So we are given M clauses, and our goal is to satisfy as many as possible rather than all of them. Okay, so is the problem okay? This is just 3-SAT viewed as an optimization problem. And again, it's a very useful optimization problem, just like 3-SAT is a basis for NP completeness or NP hardness, or talking about the complexity of many problems. This optimization version is used as a basis for understanding lots of other optimization problems, or how well we can approximate them, etc., etc. So, and a simple property to show is that there exists a way of assigning these variables to true or false, such that it satisfies at least 7 M over 8 clauses if you had M clauses in the original formula. Okay. So for each variable, there is a choice to set it to true or false. I don't know which, but that together these choices satisfy at least 7 M over 8 clauses. Okay. And the proof is sort of just an application of the statement we made about expectations. So let's set up our omega. Let's define a random variable x of omega, and in this case z of omega, and then then see how to apply the statement we talked about. So let's say omega is that we're assigning all the variables to true or false independently at random with probability half each. So you can think of omega as the set of all assignments to all variables. So each outcome is a collection of values for all variables. Okay. So it's a set of size 2 to the n. And because all of these are independent and uniform, for every outcome, we have the same probability, 1 over 2 to the n. And the random variable we are interested in is the number of satisfied clauses. So once I tell you all the variables, you know all the information you need to go to every clause and see out of the 3 variables are the values assigned in such a way that the corresponding clause is satisfied. So in particular, if you wanted to check the first clause, you should check is x1 true, or is x9 false, or is x2 true. If any one of these 3 things happened, you're good to go. And if the clause 1 is satisfied. So by satisfied, I just mean that it evaluates to true as a function of these 3 values. And so on. So Z is a function of outcomes. Once I tell you an outcome or the value of all the variables, you can compute Z. In particular, you can actually go and compute for every clause. Another way of saying that is that you can write Z as a function of random variables y1 to ym, where ym or yi rather is 1 if the ith clause is satisfied, and 0 otherwise. Okay. And since I wrote it like this, you know that we're going to use linearity of expectations. So and now what remains to be done is compute the expectation of this one random variable yi. Again, notice that y1 to ym are not necessarily independent random variables. There can be 2 clauses which involve the same variable x1, or maybe they involve x1 and x3, but some other variable which is different. So they can be sort of dependent on each other in some weird ways, but we don't need independence or anything really to apply linearity of expectations, certainly when we have finite outcome spaces, etc. So all we needed is that you can write Z as a sum of y1 to ym. Once you have this, expectation of yi is a relatively easy thing to compute. So yi is just dependent on 3 variables, right? So so there are 3 things. At least one of them has to happen for yi to be 1, or expectation of yi is that at least one of these 3 things happens. Either li1 is true, which means some variable is either true or false depending on what li1 is. Same for li2 and same for li3. And now each of these 3 things sort of can be true or false with probability half each. They are independent. The probability that at least one of them happens is 1 minus the probability that all 3 of them don't happen, and the probability of kind of li1 being false is 1/2. The probability of li2 being false is 1/2. The probability of li3 being false is 1/2. So this is 7 over 8. And by linearity of expectation, this is 7m over 8. So the expectation of z is 7m over 8, which means that there exists at least one omega, and omegas are just assignments to the variables. So there exists at least one assignment such that z of omega, which is just the number of satisfied clauses corresponding to this assignment, is at least 7m over 8. May not be exactly, but at least. Is that okay? Any questions? Okay. And this can also be turned into an algorithm relatively easily, although again, yeah, I just mean to illustrate it that it's not always that it's kind of difficult to construct these things, and sometimes the proof can be used to actually design an algorithm. It sort of has a grandiose name called the method of conditional expectations, but it's actually a very simple thing. It's again an application of total probability. So what we wanted to compute in this case was expectation of z, and we know that this is greater than or equal to 7m over 8. The probability of x1 being true is half. The probability of x1 being false is half. So we know that there exists some value for x1, that the expectation of z conditioned on this value is at least 7m over 8. Again, we have an average of two things. The average is bigger than 7m over 8. At least one of the two things is bigger than 7m over 8. Okay. And I claim we can actually calculate relatively efficiently which one. So as an exercise, you can look at the formula and calculate the expectation of what is the chance that a random assignment satisfies any given clause. Okay. We just saw that in general it's 7m over 8, but even if I fix x1 to be either true or false, I can go back to your formula again, go back to every clause. If that clause involved in x1, great. The probability that a random assignment satisfies it is 1 because it's already satisfied. We set x1 to true. If the clause involved x1 is equal to sort of negation of x1, and I did decide to choose x1 to true, go back to that clause, basically remove x1, because the only way it's going to be satisfied is one of the other two variables is assigned in a way that it's satisfied. x1 is a lost cause. I mean, the clause wanted it to be false, and it's set to true. So you can go to every clause and just look at what is the chance that a random assignment satisfies it, even conditioned on fixing some of the variables. So I claim that you can efficiently evaluate what is the expectation of z conditioned on x1, basically because you can efficiently evaluate what is the expectation of each yi conditioned on x1. And then we basically recurse on this. So if I can evaluate the expectation of z conditioned on x1 equals true and evaluate this expression on x1 conditioned on x1 equals false, I know that at least one of them will be bigger than 7m over 8. Whichever is bigger, I computed both these numbers. I will assign x1 so that I get the bigger of the two values. So let's say the conditioned on true expectation of z was at least 7m over 8. Then I will just choose the value true for x1 and look at my new collection of clauses and do the same argument. Conditioned on now x2 is equal to b2, you can show that one of the expectations will be bigger than 7m over 8. And the fact that I can, and again, I can evaluate conditioned on x1 equals true and b1 and x2 to be whichever of the two values you are interested in. So you can show that the same is true when I want to look at conditioned on x1 equals b1, x2 equals b2. And I can also compute expectation of Z conditioned on x1 equals B1 and x2 equals B2. I'm not considering all possible choices for B1 and B2 and so on simultaneously. First, I'm considering choices for B1. Then I fix B1 and I only consider 2 choices for B2. Then I fix B2 and I only consider 2 choices for B3s and so on. So in general, I'm only considering I'm doing this whole thing 2n times. And every time I do this, I can do it clause by clause. So I can do this in time, which is linear in the size of the formula or the number of clauses. But okay, again, don't need to worry about the exact complexity of this algorithm. But just to say that here, it can be turned into an efficient search algorithm by just kind of staring harder at our proofs. And I'll write more details in the notes in case you're interested. Any questions? Okay. Sorry, we're out of time. So let me just skip the next application and quickly, just in a couple of minutes, go over the midterm. And I'll stay on after the lecture in case you have any more questions. Just to remind you, problems in the midterm. The first one was if you have a map, a linear map from V to W, if you start with V1 to Vk, which are linearly independent, is it true that the phi of V1 to phi of Vk are also linearly independent? And I mean, you can create many examples, but just the simplest example maybe is to just take the linear map to be always 0. It's a linear transformation. And of course, if you map linearly independent things to 0, they are no longer linearly independent. Another question was, if you have 2 linear transformations or linear operators from the same space from V to V, and their images are equal, then is it also the case that their kernels are equal? And yeah, I mean, there was, I think it was already discussed in one of the problems in the homework. So you'll see that reference in the graded midterms. I don't remember exactly problem number, but I mean, here's an example. So think of 2 linear maps, one of them, like these are both on 2-dimensional space. Both of them kind of give an output where only the first coordinate is non-zero, the second one is 0. But one of them kind of takes the first coordinate of the given vector and copies it as the first coordinate of the new vector. The other one takes the second coordinate of the given vector and copies it as the first coordinate of the given vector. So in one case, you kind of take the y coordinate and write it in the x position. In the other case, you take the x coordinate, write it in the x position, and set the other one to 0. The images are the same. The images are just all vectors with the first coordinate non-zero, and the first coordinate arbitrary and the second coordinate 0. But kernels are different. In one case, the kernel corresponds to things where first coordinate is 0, second is non-zero. In the other case, it's about the first coordinate. You can check. So it's but again, any example you gave is fine. It's this is just one simple example. The third one is this kind of polynomial evaluation and in a product where you sum p of I, q of I, and you need to check linearity. It's sort of clear from the expression that it's linear, and you can write it out in more detail. The fact that it's symmetric here, because everything is real valued, there is nothing anything interesting going on. It's just by looking at the expression, it's remains unchanged if you exchange p and q. The third one was an interesting one where we need to show that, well, a it's greater than or equal to 0. That's easy because it's the sum of squares of real numbers, which is greater than or equal to 0. And it's only 0, or it's 0 if and only if the polynomial is the 0 vector, or rather the identically 0 polynomial. And here we use the fact that, and this is something that maybe some people miss, that, it's equal to 0 if and only if the polynomial evaluates to 0 at all these 7 points, but it's a degree 5 polynomial. It cannot evaluate to 0. It cannot have 7 roots unless it's the identically 0 polynomial. Kind of a non-zero polynomial of degree 5 can have at most 5 roots, so cannot be 0 at 7 points. Okay. So this was maybe only sort of non-trivial observation in this. Part 2, I mean, a bunch of information is given. There's kind of an inner product mu1 that you are given. We know that phi is self-adjoint. Self-adjoint for this inner product. Remember that adjointness depends on the inner product, and we saw this also in the homework. And you are given W1, W2, which are independent eigenvectors with different sort of orthonormal eigenvectors, again, with respect to this inner product and with the distinct eigenvalues. And some other linear transformation which maps W1 and W2 in some weird ways is what we'll get to that. And then again, mu2, which is defined as a new inner product. First question is, are W1, W2 still a basis of eigenvectors? Full points for saying duh, because I mean, the concept of independence and eigenvectors don't depend on the inner product. So of course it's true. W1 and sort of our W1 and W2 orthogonal. They're not, and you can check based on the fact that the W1, W2 are orthogonal according to mu1, and mu2 can be written in terms of mu1. So you can write it out and check. And part C is, I didn't write the question, but part C was that is phi still self-adjoint with respect to this new inner product? Again, you can say, check it in a variety of ways, but one slick way of saying is that we know eigenvectors corresponding to different eigenvalues are orthogonal for self-adjoint operators. We know that W1 in part A, we saw W1 and W2 are still eigenvectors corresponding to distinct eigenvalues lambda1 and lambda2. And in part B, we did say that they are not orthogonal. So phi cannot be self-adjoint. But yeah, any other method of solving this is also fine. For the third problem, it's sort of again this kind of averaging argument that if you have an approximate eigenvalue which is defined as some lambda such that phi of v minus lambda is less than or equal to epsilon for some v, let's say, of norm 1, so that kind of the normalization is correct for the epsilon. We want to show that there exists an eigenvalue mu which is close to lambda, and here we assume that lambda was a real number, mu are real numbers because the operator is self-adjoint. You don't need to, but actually it simplifies the problem, and it was given in the problem, so why not? It's a self-adjoint operator, so one clean way of thinking about it is let's start with an orthonormal basis of eigenvectors. Once you have that, you can write the norm of v as summation ci, sort of in terms of the coefficients, just the squares of the coefficients, and that is 1. And you can write the norm of phi of v minus lambda whole squared as some sort of summation of mu I minus lambda whole squared, weighted by these coefficients ci squared. Again, these coefficients sum up to 1. So if the average is greater than equal to epsilon, is less than equal to epsilon squared, then at least one of the terms appearing in the average, which is mu I minus lambda whole squared for some I, should be less than equal to epsilon squared, and then we are done. So, I mean, again, there are many possible ways of solving the problem. If you give any other solution, that's fine too. And let me know if you have any questions. I'll stop here and I'll stay on if you have any